Hey guys, so this video is part 2 of electron configuration, and as you can see on the right, I have a copy of the periodic table because you are going to want a copy of your periodic table in front of you. You can also use the one in the video, but it will be really helpful for you to have one of your own. So there are 3 rules that we need to talk about with electron configuration, and for the sake of like your test and things like that, you're not going to have to remember their names, but you do need to understand the principles. They're pretty basic. So the Pauli exclusion principle says that no electron can occupy the same space. And so what that means is you can't have 2 electrons in the exact same spot. They have to be in different locations. They can't sit right on top of one another. And so that means each of these boxes on the periodic table has to represent only 1 electron, not 2. And the Aufbau principle says that electrons are going to fill in the lowest energy level first. And so that means energy level 1 is going to be filled in before energy level 2. Energy level 3 will be filled in before energy level 4. And that is also why this D sublevel, which in this case are all of these lovely yellow boxes here. Remember, the D sublevel, you subtract 1 energy level, and because Aufbau says that it's going to fill in the lowest energy first, 4s, so this group, is actually lower than the 3ds because the sphere is more simple than that complicated D level shape. And then Hund's rule says that every orbital has 1 electron in it before the second is added. So that means that, for example, the P sublevel, if you think of the 3 boxes as being the 3 orbitals, that means each box has to have 1 electron before the second one can be added. And so we'll do some work with diagrams that can help us with this idea, but that is what it says. So when we do electron configuration, the electron configuration, or the full electron configuration, is represented by all of the electrons that are included in that atom. So the first one we look at is lithium. And lithium is right here on our periodic table. It's number 3. And in a neutral atom, and all of these first ones are neutral, mean that it has 3 electrons to match its 3 protons. So it means it covers the box for hydrogen, helium, and lithium. And so the way you write the electron configuration is you read the periodic table like a book. So you start at the top and you read from left to right. So when I first read, I hit energy level 1. I hit the S sublevel because these are S, D, and P. And so in that S sublevel, I have the hydrogen box and the helium box because helium kind of goes here. So that would be 1s2, and that covers that whole first row. And then I also read the second row, so the second energy level is also S, and lithium is the first one there. So I put the 1, and I'll stop because I've reached my address or the destination for lithium. So lithium has two orbitals, the 1s and the 2s, has 2 electrons in the first, 1 electron in the second. And so with carbon, we do the same thing, but we kind of start from scratch. So carbon is right here, it's number 6. And so again, we read the periodic table like a book. So we start at row 1. So we would have 1s2 because that takes care of hydrogen and helium. And then we get to 2, and we have 2s, We have lithium and beryllium are both included, so that's 2s2, because when we keep going across row number 2, we hit a new sublevel. We hit the p's, and so this would be 2p, and boron and carbon, that's 2, so it'd be 2p2. And then for sodium, it would be similar. We would keep going all the way to sodium, so it matches. It's 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, all the way to neon, so 2p6. And then we look at row 3, and sodium is on row 3, sublevel S, and it's the first box, so 3s1. And so it keeps going through all of that. And I want to do vanadium, number 6, as an example, because this is where you see that energy level thing happen. So again, it's the same as sodium, 1s2, 2s2, 2p6, and then when we get to the 3 s's, vanadium is number 23, so we're going to hit sodium and magnesium, so 3s2, and then we keep going across, and we hit the 3 p's. We have 3p, 1, 2, 3, 4, 5, 6, so 3p6. And then we go to the 4th row, and we hit 4s, and that's 1, 2, so 4s2. But now that we're in the D sublevel here, okay, we have to subtract an energy level. So it actually goes back to 3D, 1, 2, 3. And so for the most part on a test, you would only have to do the elements that are in rows 1 through 4. Very, very rarely would we ask you to do something in 5, 6, or 7. So for example, francium, Fr, that's kind of a challenge question for you, and I'd love to see what you come up with it. And one thing from this that we learn is earlier we talked about valence electrons, or those electrons that are on the outer energy level. And one way that you can look at that is we can look at the energy level that's on the outside, and we see, okay, the 2 is the highest energy level here, and it's 1. So it has 1 valence electron. And then for carbon, we've got the highest energy level is 2, and it's 2 plus 2 is a total of 4 valence electrons. And sodium, the highest energy level is 3, and there's 1, so there's 1 valence electron. And what that helps us see is if you look and zoom in on our periodic table, and I'm going to go ahead and erase all of this so we can see it more clearly, is there's a pattern that comes about. Everything in this first column, column 1, is S1. And then everything in the second column is S2. And so if you have something in that first column, you're always going to have 1 valence electron. The second column, you're going to have 2 valence electrons. And we kind of skip over the D sublevels because depending on the element, they can change as to whether or not these are the valence electrons or these are the valence electrons. Remember, electrons are like teenagers. They don't always like to follow the rules. And then over here, we can see that everything here is in the P1 sublevel. And so whether it's 2p1, 3p1, 4p1, 5p1, 6p1, 7p1, and it's column number 13. Well, that's because it includes S1, S2, and P1. So that's 3 valence electrons, and it increases 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. And the reason why this is important is because when we talk about cations, which have a positive charge, because remember, cats have pause, and so cations are positive. This means that they lose their electrons. Okay? They have more protons than they do electrons. Some of their electrons are gone. And anions are negative, and that means that they've gained some extra electrons. And so the reason why cations and anions even form is because of these valence electrons. There's a rule called the octet rule that says that all atoms either need to have 0 or 8 valence electrons. Essentially, they need their outer energy level to be completely filled. So they do that by either losing electrons to drop to a full inner layer, or they add more energy or more electrons to just fill up whatever's the rest. But they do it based on what would be easiest. And so we can see that if I have one valence electron, I can either lose 1 to get to 0 or gain 7 to get all the way to 8. So they always lose. And so essentially here, all the way to 3, all of these are going to be cations because they're all going to lose valence electrons in order to become positive. And then anything that's higher than 4, so 5, 6, and 7, so 5, 6, and 7, these are going to be our anions. So you can see there are a lot less anions than there are cations. If it's in column 8, then column 8 is already stable. It has 8 valence electrons. It doesn't need to gain or lose any. And then this column here, column 14, it can be both depending on the situation. And so that's why these valence electrons are important. It's why our electron configuration is important, and it's why it's important to recognize the valence electrons. So you can tell that based on where they are, or you can look at their electron configuration. And so for example, if we look down at some of these ions, we know that cations are going to lose electrons, and this should say anions are going to gain valence electrons. We're going to add lose valence electrons here. And so remember, our cations are positive and anions are negative. And so when we look at calcium, calcium normally has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, because calcium says it has a positive 2 charge, that means it's going to lose 2 of those valence electrons, and it's the one very outside. So that means instead of being 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, it's going to lose those outer 2 electrons, so that means the 2 from 4s are gone, so it actually goes down to 3p6. And so lithium does the same thing. It's normally 1s2, 2s1, but because it's positive 1, it loses that outer electron, and so now it's down to 1s2. And we can see the same for the anions, except they gain. So sulfur is normally 1s2, 2s2, 2p4. And so you can see it has 6 valence electrons right now. It needs 8. That negative 2 tells me that it gains 2 electrons. So now instead of being 2p4, it becomes 2p6. And so it just gains or loses the number of electrons based on what the charge is and what it needs to fulfill the octet rule. So hopefully this has been a good review for electron configuration for you. And the key thing with electron configuration, guys, is practice, 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 practice. Always practice, and then practice a little bit more. Good luck.